Hello everyone, my name is Emiliano Larach, and today I'm going to be going over lab number 5, which is Choose Your Own Adventure, and I will be studying the movement of a slinky. I'm in Dr. Fabio Fenton's class, Physics 2211. First, the purpose of this lab is to create a computational model that predicts the motion of a fallen slinky using Newton's second law and other concepts that we have studied throughout the semester. Our model's motion should follow the same dynamics as the actual slinky. So what are the dynamics of this system? So when the hand lets go of the slinky goes down. The bottom does not move until the compressional wave travels to the bottom and moves it. So until the point where the slinky is not moving here at the bottom, the forces acting on the slinky are only the force of gravity and the force of tension, and they each cancel each other. That's why the bottom of the slinky does not move. When the compressional wave caused by the hand removing the tension from the slinky travels all the way to the bottom of the slinky, now we don't have anymore the force of tension. So the slinky falls, and we have the force of gravity and the force of drag created by the air. Some fundamental concept for this lab will be the momentum principle, as we know, Newton's second law and its velocity update formula, the force of tension, which we only need to know that it's equal to the force of gravity when the system is at dynamical equilibrium, the force of gravity, which we can calculate as mg, and the force of drag, which is our constant b that we calculated by trial and error, times the magnitude of the velocity squared. The initial conditions for our system were the slinky mass was 0.218 kilograms, the slinky extended length was 1.365 meters, and the initial position was the one you can see on the screen. Both of these data for the slinky are standard, and we found them on the internet. The initial position was the one given by tracker. In our tracker data, we can observe how the slinky moves. So the slinky stays stationary, the bottom of the slinky stays stationary until the compressional wave that was caused from the man letting his hand not holding the slinky anymore reaches the bottom of it. The time when the bottom started moving was 3.2 seconds, and the initial position, as I said before, was the one that you can see on the screen. As we can see here, the slinky starts moving until the compressional wave reaches the bottom of the slinky. For our initial conditions, we talked about the slinky mass and the force of gravity. Also, the j hat vectors is just the movement in the y direction, and the b we found it using trial and error to be 20.55, which is our coefficient of drag. Then, for when the bottom of the slinky is not moving, when it's at dynamical equilibrium, we just counted two forces for our Glowscript code, which is the weight force that you can see I'm signaling with my pointer, and the force of tension, which is just the positive of the weight force of the force of gravity since it's not moving. So the net force, we just add these two up. For the part when the bottom of the slinky start moving, it means that the compressional wave reached the bottom of the system, so it falls. So now for a weight, we have the same one, mgh, and also the force of drag is just b times the magnitude of the velocity squared times j hat. So our net force is just adding those up. Our results, we can see that they're practically identical. They just diverge a little bit here, and that could be just because other forces that are not taken into account. Maybe the hand moved a little bit, or just a current affair was passing and it messed something up, so it's normal to see this kind of deviations. We can see here in our Glowscript code how it doesn't move until 3.2 seconds, which was our mark when the slinky started moving, and we can see that the bottom doesn't move until the compressional wave reaches the bottom of it. Does the bottom of our model slinky stay stationary just like the video? Yes, it does. As we saw in our model, it stays completely stationary until the compressional wave reaches the bottom. The bottom of the slinky, as a conclusion, does not move until the compressional wave that was unleashed at the top reaches the bottom of the slinky. In our screen, we can see an example on how the hand creates a motion, a vibrational motion, and we can see how it travels as a wave. So this was exactly the same we can see. So the motion of the hand gets translated through the coils until the end. I hope you enjoyed this lab, and I hope you really understood how the motion of the slinky works. Bye.